Hello and welcome. What spawned this video was the recognition that the findings within quantum physics inevitably are linked to the spiritual awakening that is happening on the planet. Therefore, there's naturally a lot of talk about quantum physics, and yet, at the same time, most struggle to say what it actually is. First and foremost, it's good to know a little about the mechanics behind what one is doing and interacting with, simply because such knowledge usually comes in handy in one way or another, and because what one experiences becomes more tangible, even if many authors stress that the techniques they teach work regardless of whether one understands how they work or not. Secondly, scientific materialism still has a strong foothold. This means that, even though many of us know that the world is much more than can be perceived with the five senses, this is yet not the reality most live in, and many who just are waking up may still not know what to believe. Therefore, claims will be met with challenges, and valid ideas may be dismissed as woo-woo if the rationale behind them cannot be properly explained. It will be necessary to begin with a very basic explanation that doesn't even begin to explain the field, and then work from there. Quantum physics is the branch of science that delves into the behavior and nature of matter and energy at the most fundamental level, at the scale of atoms and subatomic particles. At this microscopic scale, the physical rules that govern larger objects, described by classical physics, like Newton's laws of motion or Einstein's relativity, no longer apply in the same predictable way. Instead, the universe operates by an entirely different set of principles that often seem strange and counterintuitive to our everyday experiences. The term quantum originates from the Latin word quantus, meaning how much. It encapsulates a fundamental idea that lies at the core of quantum physics. Energy and matter are not endlessly divisible. Instead, they exist in the form of discrete, indivisible units known as quanta. In classical physics, it was long believed that physical properties like energy, light, and even the position of particles changed smoothly and could be divided into infinitely smaller portions. This view suggested a continuous and uninterrupted nature of reality. However, the discovery of quanta introduced a groundbreaking shift in this perspective. It revealed that, at the most fundamental levels of the universe, physical properties appear in specific, finite amounts rather than in a seamless flow. Essentially, quanta represent the smallest building blocks of energy and matter. This realization not only reshaped our understanding of how nature operates at microscopic scales, but also laid the foundation for much of modern physics, leading to technologies and insights that have transformed the way we view the universe. Quantum physics began to take shape in the early 20th century, as scientists like Max Planck, Albert Einstein, Niels Bohr, and Werner Heisenberg grappled with puzzling experimental results that classical physics could not explain. For example, light was found to exhibit behaviors that defied classical wave theory, leading to the realization that it sometimes behaves like particles, now called photons. Similarly, electrons and other subatomic particles displayed bizarre behaviors, appearing to exist in multiple states or places simultaneously, or interacting across vast distances instantaneously. For perspective, it could be interesting to note that even though the idea of the atom had existed in philosophical writings since around 500 BCE, it wasn't until 1803 that the English chemist John Dalton laid out evidence for it. What he proposed was that matter is indeed made up of indivisible atoms, each unique to a particular element. This then laid the groundwork for understanding chemical reactions, suggesting that atoms combine in fixed ratios to form compounds. This marked a significant step in establishing the atom as a fundamental building block of matter. However, it wasn't until the 1920s that scientists began seriously exploring the quantum world, and new findings are made constantly, such as the discovery of quarks in the 1960s. What this means is that this science is fundamentally reshaping everything we think we know about the nature of reality, consciousness, and our understanding of our place in the world, and it may just be in its infancy. Therefore, All things considered, it's probably wise not to dismiss anything that comes from outside the scientific community. We are, after all, looking at a world that may be approached from many other angles than scientific experimentation, such as, for example, different techniques that are for the most part labeled spiritual, even if such terms admittedly come with their often detrimental baggage. This new realm of physics has given rise to ideas such as the interconnectedness of all things, the probabilistic nature of physical laws, and the fundamentally indeterminate structure of the universe. If you're familiar with more esoteric teachings, you will, for example, see that the idea of the interconnectedness of all things is found in works such as the Emerald Tablet, which was written somewhere between 200 and 800 AD, and later expanded upon in more modern works, such as the Kabbalion. At its core, quantum physics challenges the notion of a fixed, deterministic universe. It suggests that at the smallest scales, the universe is governed by probabilities, uncertainties, and dynamic interactions that are only partially knowable. This has led to different teachings and philosophical debates about the nature of reality, consciousness, and the role of observation in shaping the universe. As mentioned, in the quantum world, particles like electrons and photons can exhibit both wave-like and particle-like properties. This means that, depending on the experiment, they might act like tiny billiard balls or like ripples in a pond. This dual nature is fundamental to quantum physics. This idea has led to speculation about the observer's effect on reality. It has also been referenced in spiritual teachings, such as the law of attraction. The ripple effect reinforces the belief that small changes can lead to significant outcomes, which some claim can be applied consciously to achieve goals. Electrons, which are subatomic particles that orbit the nucleus of an atom, are typically thought of as discrete, point-like objects. However, under certain conditions, they reveal characteristics that resemble the spread-out, undulating patterns associated with waves. Photons, which are the fundamental units of light, share this same duality. They can appear as individual packets of energy, akin to particles, yet they are also capable of forming interference patterns and diffraction, both hallmarks of wave behavior. Diffraction is a phenomenon that occurs when waves encounter an obstacle or pass through a narrow opening and bend around the edges instead of continuing in a straight line. This dual behavior means that when scientists design experiments to measure electrons or photons, the outcome can vary dramatically based on the setup. In some cases, electrons will leave marks on a detector screen as if they were tiny projectiles fired from a slingshot, traveling along a straight path until they strike a surface. At other times, when passing through narrow slits or encountering barriers, electrons produce patterns of alternating light and dark bands, a sign that they have spread out like ripples on water, interfering with themselves. Similarly, photons can strike a metal plate and dislodge electrons in a way that suggests they are localized particles transferring energy upon impact. Yet, when photons pass through a pair of slits, they generate complex patterns of interference that suggest they traversed both slits simultaneously, much like waves moving through two openings and overlapping to produce areas of reinforcement and cancellation. This dual nature is not merely a curiosity, but lies at the very foundation of quantum physics. It challenges the classical notion that particles and waves are distinct and separate categories. Instead, electrons and photons seem to belong to a deeper, more fundamental layer of reality, where the rigid boundaries between particles and waves dissolve, revealing a strange, fluid interplay between the two forms. This interplay forces us to reconsider how matter and energy exist at the smallest scales, underscoring the idea that the universe operates by rules that defy our everyday experiences. Now, after this presentation, let's look deeper at some of the most important terms. We've already touched upon quanta, and we will now look a bit deeper at the subject. To reiterate, quanta are the smallest indivisible units by which certain physical properties, such as energy, light, and matter, manifest at the most fundamental level of nature. The existence of quanta was first proposed by Max Planck in the year 1900 when he sought to solve the problem of blackbody radiation, a puzzle concerning how objects emit light and heat. Classical models predicted that the intensity of radiation at short wavelengths should increase indefinitely, but experimental results contradicted this. Planck suggested that energy could only be emitted or absorbed in specific, finite amounts, which he called quanta. This simple but radical proposal laid the foundation for quantum theory. Quanta challenged the prevailing belief that energy transitions smoothly. Instead, they revealed that processes at the microscopic level occur in distinct jumps. For instance, when atoms gain or lose energy, they do so by absorbing or emitting whole quanta of energy, never fractional amounts. This explains why atoms only emit light at specific wavelengths, resulting in the characteristic spectral lines seen in atomic emission spectra. The most important takeaway for this discussion is that the discovery of quanta marked a turning point in science, revealing that at the smallest scales, nature adheres to rules vastly different from those governing larger, macroscopic objects, and that this changes everything about what we think we know about how reality works. This leads us to one of the most intriguing aspects of quantum physics, superposition. It suggests that particles can exist in multiple states simultaneously until they're observed. A famous thought experiment illustrating this is Schrödinger's cat. In this scenario, a cat is placed inside a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, killing the cat. If the atom does not decay, the cat remains alive. According to quantum theory, until the box is opened and observed, the atom exists in a superposition of decayed and non-decayed states. Consequently, the cat is considered simultaneously alive and dead. This paradox highlights the unsettling idea that quantum states depend on observation, raising profound questions about the role of measurement and the nature of reality in quantum physics. If true, this thought experiment shows that reality, until observed, merely exists as an infinite number of possibilities that collapses into one single scenario upon observation. In a cold, random universe that is merely the result of chance, this may not have any practical consequences whatsoever. However, in a meaningful universe, where everything has a purpose, this may change everything about how we may relate to our being in the world. Another important term within quantum physics is quantum entanglement. Quantum entanglement occurs when particles become linked so that the state of one instantly influences the state of another, no matter how far apart they are. Albert Einstein famously referred to this as spooky action at a distance. Entanglement is a key resource for emerging technologies like quantum computing and quantum cryptography. And it also happens to align with the principle of correspondence within Hermetic philosophy and other esoteric teachings. The esoteric notion of as above, so below mirrors this concept by implying that actions or states in one plane of existence reflect or influence those in another plane. Just as entangled particles seem to know what happens to their counterparts instantaneously, the principle of correspondence suggests that shifts in the spiritual or mental realm can manifest in the physical world and vice versa. This principle posits that patterns and laws observed in one level of reality can be found mirrored in another. For instance, the microcosm, individual or atomic level, reflects the macrocosm, universal or cosmic level, and vice versa. Understanding this interconnectedness allows individuals to gain insights into higher realms by studying the lower, and to comprehend the lower by understanding the higher. While the mechanisms behind quantum entanglement are rooted in measurable physical interactions, the principle of correspondence applies more broadly to patterns and archetypes across different layers of reality. However, both suggest a hidden unity and deep connection beyond the planes of time and cause and effect, underlying the apparent separations in the universe. Next, the uncertainty principle, formulated by Werner Heisenberg in 1927, is one of the most profound and counterintuitive discoveries in quantum physics. It fundamentally challenges classical ideas about how precisely we can measure and predict the behavior of particles at the smallest scales. The uncertainty principle tells us that there are limits to how well we can know two things about a particle at the same time, such its position and its momentum, how fast it's moving. The more accurately we measure one, the less we can know about the other. This isn't just because our tools aren't good enough, it's a fundamental aspect of how the universe works. To explain why, let's imagine trying to see an electron by shining light on it. Light is made of photons, which are tiny particles of energy. If we use light with very short wavelengths, like X-rays, it can give us a clearer view of the electron's exact location. But short wavelength light has high energy, and when it hits the electron, it can knock the electron around, changing its speed and direction. If we use light with a longer wavelength, like infrared, it won't disturb the electron as much, but it also won't show us precisely where the electron is. However, the uncertainty principle is not just about the light interfering with the electron. Even if we tried to observe the electron in some way that didn't involve photons, the uncertainty would still exist. This is because, at the quantum level, particles like electrons don't have a definite position and momentum at the same time. Instead, their properties exist in a range of possibilities until they are measured. The act of measuring collapses these possibilities into one outcome, but in doing so, it disturbs the balance between position and momentum. So, the uncertainty is not just caused by light knocking the electron around. It arises because the electron itself exists in a state of uncertainty. The measurement process doesn't just reveal information, it also changes the nature of what is being measured. Finally, let's look at quantum tunneling, which shows how particles can overcome barriers that, under classical physics, they shouldn't be able to cross. To understand this, imagine rolling a ball toward a hill. In classical physics, if the ball doesn't have enough energy to climb over the hill, it will simply roll back down. However, in the quantum world, particles like electrons or protons don't behave like ordinary balls. Instead, they are described by wave-like properties. These quantum waves represent the probability of the particle being in different places. When a particle approaches a barrier, its wave doesn't stop abruptly at the edge. Instead, part of the wave continues to extend beyond the barrier, even if the particle doesn't seem to have enough energy to pass through. This extension means there is a small but real probability that the particle will appear on the other side of the barrier, as if it tunneled through. It's as if the ball, instead of climbing over the hill, somehow disappears and reappears on the other side without having crossed the top. The size and likelihood of tunneling depend on the height and width of the barrier and the energy of the particle. The thicker or taller the barrier, the lower the probability of tunneling. Quantum tunneling isn't just a theoretical oddity, it plays a crucial role in the universe. In stars, it allows protons to overcome electrostatic repulsion during nuclear fusion, enabling the process that powers the Sun and other stars. Without tunneling, the temperatures and pressures required for fusion would be far greater, making stellar formation much less likely. This is yet another example of how energy behaves unpredictably at the quantum level. In summary, quantum physics reveals a reality that is far more intricate and interconnected than classical physics ever suggested. At the subatomic level, particles exhibit wave-particle duality, existing as both matter and energy depending on how they are observed. Concepts like superposition show that particles can exist in multiple states at once, while entanglement demonstrates instantaneous connections between particles across vast distances. The quantization of energy and the uncertainty principle highlight that nature operates in discrete probabilistic steps, challenging the deterministic view of the universe. Remarkably, the act of measurement, or observation, appears to play a role in determining the state of particles, suggesting that consciousness or the act of inquiry might be more deeply woven into the structure of reality than previously thought. What all this seems to point to is that consciousness cannot be separated from reality, and that many of our foundational assumptions about how the universe works collapse at a quantum level. Hearing this spelled out in a YouTube video may not do much for you until it truly sinks in that this changes everything about how we look at reality and our relationship with it. At the same time, it's important to realize the limitations of language. We should not assume that we understand the meaning of statements such as consciousness is the foundation of reality, or the observer cannot be separated from the observed, and even less so when it comes to the implications of such statements. Therefore, if any of this rouses your interest, you are invited to explore these concepts on your own, while being wary of drawing unwarranted conclusions. This video can, at best, be a very small starting point. You've now reached the end of the video. Remember to like and subscribe. Thank you for your time.